I'm Shivji, and together with Sachidanand, we will be talking on streaming wars and how Apache Pulsar is acing this battle among the various streaming frameworks. I am a staff engineer at Nutanix. I lead the cloud data platform team there, where Sachidanand also works with me. And we love open source, we love distributed systems, and I am a complete data geek. I started working out with MySQL, and then Kafkas and Pulsars of the world. And then now I also support analytics. And all of these are products that we provide as a service, backing multiple Nutanix products. Previously, I have also contributed to Pulsar source code and MySQL source code, among others. And in this talk, actually, we will be covering a lot of details. So if you want to know some of those in more detail, you want to go deeper, you can watch some of my previous talks, which is linked from here. Sachidanand, can you introduce yourself, please?
Sure. Hi, everyone. This is Sachidanand. I am also from Nutanix Cloud Data Platform team. I am currently working on streaming platforms like Pulsar and online analytics database platforms like Druid, which backs various Nutanix products. Yeah, let's go.
Great. So now we'll go to the legal disclaimer, but the summary of it is just that, whatever we present here is our own view, and we don't represent Nutanix stand on anything here. So moving on to the agenda, by the way, one fun bit is that because we have this whole spirit of a battle here, we have used the Avengers theme, and I hope we can have some fun with these coming to the end of this conference. So talking more technically on the agenda side, we will very, very quickly look at what is streaming or messaging. And then we will look at what requirements you can have from a streaming framework. You could have maybe a couple more requirements or a couple less requirements than ours, but it will more and less be similar only. The choices of frameworks out there in the market today will sort of focus on some really popular ones. And then we will tell you why we love Pulsar and NATS. We will look at the ecosystem around these frameworks as well. And then we will tell you our learnings from it as well. And then Sachin will finish the talk with some demos. Introducing the streaming, we have producers here. It puts a message in the messaging framework, and then it gets consumed by the microservices, which could keep it to themselves, or it could sync it to a big data store. Amenities of this game, right? So if you go on a battle, you want to have your tools sharpened. You want to have the best tools out there. Similarly, when you want to choose a streaming framework that backs your production workload, you want it to have really the best features, so you can be prepared to ace the use cases you have in production. The first of them is real-time messaging. Today, there are some use cases where doing something quickly is actually very, very important. For instance, if you have an e-commerce app, and on the checkout page, probably there's something that's gone wrong, then you want to detect it and fix it as soon as possible. Otherwise, you really lose business for that time, or maybe your users have some problem with payments and stuff. Scalability is again very, very important, because today we have produced a lot of data via our mobile phones, IoT devices and stuff. So you really want to make your app be able to sort of work with a framework that can scale well if required. Availability is again very, very important. If your website is not available, you are effectively losing revenue for that amount of time. You can have a recovery from any disaster situation if your data is spread across the geography. Load balancing is again something that is very important. It allows you to spread across your storage and compute across the cluster judiciously, instead of some brokers being more loaded and some brokers being less loaded. And this is something where Pulsar does really well, actually, as you will see going forward. This is one thing that helps us run Pulsar at low cost of operation. But again, I mean, cost is something that is obviously very important for the infrastructure you are using. Multi-tenancy is again something that is great about Pulsar. But in general, you want multi-tenancy so that you can separate out the different use cases, run them in isolation. So if there is a lot of load in one of the use cases, only that part is stressed, and the other parts of the cluster actually work fairly well. And because Pulsar has tons of configurations, for a given use case, maybe you need a lot of availability. For other one, maybe you need a lot of consistency. You need different application factors for different use cases and stuff like that. You can do all of that at different tenancy levels. Like I said in the beginning, we will be looking at all of these different streaming frameworks, and we will mostly be covering about Apache Pulsar, Apache Kafka, Kinesis data streams provided by AWS, and then we will also look at NATS.io. So let's get ahead with the first character in this game, which is Apache Pulsar. Obviously, it's an Apache project, and it's open source. And by the way, I think it's a great attribute of using Pulsar that this is completely community driven. If there is any major change, any change in the APIs and stuff, you will generally say that like any Apache project, they send out a voting request, so you can actually have a say in how Pulsar moves forward. Pulsar is a multi-layered architecture where your storage coupled, and then you can in scale either storage or compute. You don't have to always scale everything, and that makes selecting the type of node in AWS context for us really good. Multi-tenancy is great in Pulsar, and then Pulsar has had enterprise features from day one, which is amazing because every other feature that came after that, it integrated well with all these enterprise features. For us, enterprise readiness is actually quite important, being an enterprise ourselves. So this is something that has kept us well. Because it is a very modular thing, Pulsar actually feel a little bit intimidating when you start deploying for the first time. And Kinesis, for instance, is just a click of buttons. Kafka is moving towards monolithic architecture. But the other thing that you could get a little bit trouble with when you work with Pulsar is that compared to Kafka, the number of people using Pulsar or the connectors and community is a little lesser, but by no means this is a problem, like we will show you going ahead. Introducing the character 2 in Kafka. Kafka again is an Apache project. It's open source. It has amazing system of connections, so very good connectors out there, and it's battle tested for the longest time. So it has huge community, a lot of connectors, and all those advantages that come with being there for long. But like I said in the previous slide, it has a monolithic architecture. So, storage and compute actually gets bundled. If you think of it from the AWS point of view, selecting the type of node, that is why it gets a little bit tricky. And then because of the monolith architecture, I think flexibility, at least, scaling independently and stuff, that is a bit of a trouble with Kafka. We have done extensive performance tests, and our thoughts we have recorded in the third link that you see here. And there are some nice blogs among many others that we found very good. We have put the links to all of them here, so you can go reference that. But a quick summary of all our understanding and the performance test is that Pulsar provides a lot more throughput. We found it 2.5x in our tests, a lot better published latency than Kafka, in fact, 100x in some cases. For historical rates, if you look at the architecture of Pulsar more deeply, you see that Pulsar is composed of segment-oriented architecture for every topic, every partition. So you wouldn't have the problem of some topics being hot, some topics being cold, because the storage is really spread out wonderfully in the storage tier of Pulsar, which is Bookkeeper. And that is why you will have faster historical reads. Pulsar actually is also wonderful in the fact that it open sources pretty much everything. And in case in point being schema registry, which comes open source, and it's already bundled with Pulsar's broker. Kafka, on the other hand, does not have it in the open source version. It's there provided as a service by Confluent, which is the parent organization for Kafka. And like I said earlier, Pulsar is enterprise ready, and the example being the fact that geo-replication has always been there. Affinity and namespace isolations and stuff are things that Sachidanand will touch briefly in the later slides. But geo-replication again is something that has been there for Pulsar since day one. As opposed to that, the same thing is done by Mirror Maker in Kafka's case, which I think came late, and then there are some refuges around that. Some features will not probably work that well with it. Local disk versus tiered storage is again a great win in Pulsar's favor. And like we have been talking, Kafka wins on community support and ecosystem of connectors in general. The third character in our battle is Kinesis data streams by AWS. It's available as a service. So like all the cloud offerings, it's available by the click of a couple of buttons only. Very easy to sort of get started. And obviously it requires less maintenance using cloud elasticity and stuff. And then of course, like any other AWS service, it has very good integrations with other AWS services like S3, Dynamo, or Lambda. The bad things that did not work for us, whether it is costly compared to Pulsar, I'll explain going ahead why. And the other thing is closed source. So what we love about open source is that we can get the code and we can customize it to our needs. We don't have to wait for anyone to do that. We can just sort of hack around the code and do it quickly. The third problem that we had is around flexibility. And then I have listed down some examples. There are more, but retention period, for instance, we thought you can either select 24 hours, you can have 365 days. So there are some choices, but that pinpoint thing is what we wanted, because keeping retention anything more than what you absolutely need is something that is going to be heavy on your purse. Average record size, we couldn't make more than 1 MB. The sort of Kinesis console will give you an error there. To get around that, what we had to do is that we put the messages bigger than 1 MB in S3 and put the path to that in Kinesis. And then application has those two cases where it has to detect which is the case. And then the other thing is that, for Kinesis, data will always be replicated to 3 AZs. And what that means is that in principle, it's actually good. But if you really want to be cost effective and your use case does not require you to go maybe more than 2 AZs, then it's a little bit of a problem, because it costs more to support 3 AZs. But if you sort of are well funded for this and you really want availability and disaster recovery as the maximum you can get, then this is not a problem for you. And then, like I sort of always feel with all the AWS services or any cloud service, I would say that with Kinesis data streams, I think you are getting stuck with one particular vendor. You are designing around that. So you're getting stuck in the AWS ecosystem. Another thing we actually have come to love is NATS, because of its some of the design philosophies, which I'll discuss going ahead in the further slides. But the good things about it is that it is open source. It's a CNCF incubating project. It's not a graduated project yet, but I hope it gets there. It's very simple, and it supports a lot of flexible deployments. You can literally deploy it anywhere. And the bonus it has, opposed to Kafka or Kinesis or even Pulsar, is that there's something called NATS core, where even for synchronous traffic, you can have buffers, which is something called request reply pattern. You should definitely check it out. This is something that we leverage a lot. And then this helps us support, auto scaling and those kind of use cases really well. And this is something that is, again, very performant. So you can have millions of messages per second in very sort of small commodity hardware. The Jetstream for NATS is the messaging persistence that they have come up with lately. But because it is new compared to the other messaging frameworks, It's not as mature yet, but we are very confident that it will get there soon. We have found some rough edges, especially around recovering from disaster situations and stuff. Uh, but we have solved some of those, and even the NATS community is making very, very quick releases as we speak to iron out those issues. One more issue that we actually encountered is that, for the consumer metadata like offsets and stuff, we wanted to replicate it and store durability on different servers so that we don't lose them. But if you want to do that, what happens with NATS Jetstream today is that NATS makes a raft group for every consumer application. And then if you have millions of consumers and you have millions of raft group for it, and that gets actually too noisy in the network. That's a problem that we hope to sort of address soon in NATS. There are a couple of quotes that I really connect to, and I wanted to share those with you guys. Derek is the CEO of Synadia, which is the parent company behind NATS, and he has this sort of opinion that blue chip companies are facing this challenge where they have been convinced, and I think they have been convinced by the sort of marketing of a public cloud, where it just seems like the natural thing to start in the cloud today, but then you need to now go multi-cloud, you need to go multi-geo, and as you spread out more and more, you actually start to feel it's getting costly on the infrastructure side. Also, this is not sort of something that you can deploy with restricted capacity. And that's where NATS does amazing actually. If you look at the NATS binary, the latest binary, it's literally 11.7 MB. And I checked it today on the latest version 2.9.7. So like Stuart says here in the same podcast that you can look at on this link, that NATS is a platform which will help you become truly multi-cloud and multi-location. So NATS design philosophy, and I mean, we really like this philosophy, is that it keeps its things simple. There is only one binary. It's very small, very few APIs, very easy to understand and get started with. Its deployment models are sort of, numerous. You can do so many things. You can be really agile and carry the sort of server itself anywhere on IoT, edge, or any restricted capacity environment. It's very performant. Its decentralized security model is actually quite amazing because there is no centralization of security information. It's very difficult to break through and get hold of everything for a hacker. And NATS does really well with auto detection of issues, and then auto sort of even healing. For instance, an example being, if you add a node to the cluster, there are gossip protocols, and the cluster will discover that there is a new guy in the cluster. If there is one which dies, they'll throw them out and stuff like that. And if you look at all of our experience, what we feel is that for a cloud native application, you should go for Pulsar. For an IoT edge or a mix of IoT edge and cloud, you could choose NATS because the server really is, very small. You can deploy it anywhere with super clusters and leaf nodes and stuff like that. In NATS, you can have one cluster that actually spreads across cloud and IoT and edge, and even on-prem. And with that, I'll hand it over to Sachidanand, who will take you forward and then complete the whole thing with demos. So let me stop sharing.
Sure. Hi everyone. So now let the battle begin. We are comparing different streaming choices in one of our use cases. For that, we have chosen this use case. So the rules of the game are: we need to ingest 12 TB of data per day with each message size of 2.5 MB. That comes to roughly 5 million messages per day. So the retention period for these messages are 24 hours. That the replication factor is 2. So basically we need to store 24 TB data per day. And two more constraints we have is data should be available in multiple availability zones, and our producer and consumers are in same availability zone as stream data. So for this use case, how we set up the Pulsar cluster, I have given here the schematic architecture diagram. As we can see in the third command, we are creating two group of bookies, group bookie 1 and group bookie 2. As you can see in the pink color, we have the group 1 which contains bookie 1, and we in the violet color we have the group 2 which contains bookie 2 and bookie 3. So all our storing layer for the Pulsar is bookkeeper. So we are having each bookkeeper in different AGs. And as brokers in Pulsar are stateless, we can have all the brokers in one AG, as mentioned in this schematic diagram. So to achieve less cost, we have set the affinity group of public/default namespace to primary to group 1 and secondary to group 2. So what this will do is, whenever a broker is trying to put data in bookie, it will put one copy in group 1 and the other copy in either bookie 1 or bookie 2 or bookie 3. So with this we will have less data transfer cost between the AGs. So in another case, if we have a requirement where we need brokers also in different AGs, we can use the last command. So the last command here, it will set the primary brokers for the namespaces. So the next thing we will see is how we set up the Kafka cluster. As we all know, Kafka has these same options available in replica assignment, which takes a comma separated list of preferred replicas. In the first command, as we can see 0:1. So the partition 0 of the topic A, for that the Kafka will take preferred replica as 0. So in order to have all the data available in one AG, the broker 1 should have leader of all partitions. As we all know, in Kafka the writes only go to the leader. In that way we will have all the data available in one broker, so that we will have less data transfer cost between AGs whenever the consumer consumes the data. So whenever there is a broker goes down, Kafka has the notion to restore the leadership to preferred replica. So it will try to again go through the list, and it will choose whichever comes first in the list. It will try to restore the leadership to that broker. And this is by default enabled in the latest version of Kafka with auto leader rebalance enable set to true. As we can see in our performance test which we did, we found the Pulsar cost came up to 14K. The Kafka that is managed by Amazon, that is Amazon MSK, came up to 20K, and the Amazon Kinesis came up to 28K. So this use case came from one of our internal teams which was already using Kinesis. Now we will see the breakdown of the cost. So this is the breakdown of the cost for Amazon MSK. So here we are taking 5 M5 4x large broker instances, which has 16 core CPU and 64 GB memory. Each has attached storage of 10 TB. So in total, we will have 50 TB, which will be enough for our 24 TB of data, as we are expecting data growth in the future. Along with that, we have the intra-region data transfer cost, that is between AGs. So we have 12 TB of data per day, and one copy needs to be transferred, as we have the replication factor of 2. So for 30 days, we have 12 into 30, 360 TB of data per month. And the total cost came up to 20K. For Pulsar, as we can see in this configuration, we have bookkeepers where we store the data. So that those are M5 4x large instances. We have taken 5 with attached storage of 10 TB each. So here also we have 50 TB of data, which will be enough for our requirement. And for brokers, we have chosen R5 2x large instances, and for Zookeeper, we have chosen T3 large instances. So the monthly cost came up to 7.4K without data transfer. And if we add the data transfer cost for 360 TB, it will add another 7K. So the total adds up to 14K. And for the Kinesis data stream, as our internal team was already using this one, so there we cannot put data message size more than 1 MB. So they were having one workaround. So for the workaround, they were putting the messages in S3, and after that putting the S3 paths inside Kinesis. So that has some extra S3 cost. To make up for that, I have put 180 baseline records per second as per 1 MB data. So if you see, we have buffer for growth has 20%, which is even less, and number of fan out consumers as 3. So when we set this, we have dedicated throughput for each consumer. If we increase the number of fan out consumers, the cost increases linearly. So here the total cost came up to around 28K, and here is the complete breakdown of the cost. So as we can see that in Pulsar, with some extra efforts of one-time effort of deployment, we have the less cost compared to Kafka and Kinesis. So that's why our primary selection of data for stream data is Pulsar. So now we will go ahead with some use cases where how can we migrate Kafka users to Pulsar ecosystem. For that, the first option we have is KOP, that is Kafka on Pulsar. So for this, we only need to change in the Pulsar server side. So the client doesn't need to know whether they are using Kafka client, whether they are connecting to Kafka or Pulsar. So this KOP, which is developed by Stream Native, comes handy in that place. Another flavor we have is AOP, that is AMQP on Pulsar. As we all know, like RabbitMQ, ActiveMQ, those messaging systems use AMQP protocol for their messages. To get those clients working in Pulsar, we have AOP. And we have another variant called Starlight, which is a fork of KOP, which has extra features like TLS and schema registry, which are missing in the base KOP. Lastly, we found another way, which is Pulsar adapter for Apache Kafka. This here we need to change in the client code. So in the pom.file, we have to modify the dependencies and the URLs. So this way also works, but we don't recommend this way in our use case. So we will dive little deeper into the KOP. In KOP, what it contains is an additional protocol handler which will handle the Kafka messages. Whenever we get messages from Kafka client, the Kafka protocol handler will come into picture and it will handle that. So to achieve this in the Pulsar server side, we need few config changes in the broker.conf, and we need to add the protocol handler, that is the KOP, an R file into our server in the correct path. After that, we need to change the URL. For that, I have a short demo where I will demo in my local that how we are achieving KOP in our Pulsar cluster. So I am starting with a simple Apache Pulsar binary. Here I am extracting the Pulsar binary. After that, whatever config changes we need, we will add it to the standalone.conf for our local. In the cluster use case, we will add those config changes to the broker.conf. So here I am adding the required config changes at the end of the standalone.conf. So as we can all see, I have added one extra port, which is 9092, which will be handling all the requests from Kafka client in our Pulsar cluster. Apart from that, I have the Kafka transaction coordinator enabled true for the recent versions of Kafka, and broker delete inactive topics enabled. This property we need to set to true, and here I am just overriding that existing property. So now I will go ahead with adding the KOP nar file in the right path. So for that, I am just creating a protocols directory, which I specified in the standalone.conf already. And I am copying the protocol handler.nar file. This is available in the open source. We just need to download. So here I am using the KOP implementation of Stream Native. Now I am starting the Pulsar server in my local. As we can see, it has started successfully. Yeah, let's see that the default tenants are present, and the topics list is empty for now. So now I am going to Kafka client, where I will use Kafka clients for producing and consuming. For the for producing messages, I am using a simple Maven project which I have created locally. That is the Java client. Here I have the dependency of Kafka client, which will produce messages to our KOP enabled Pulsar cluster. So as you can see, I am just producing this test message, which will be consumed by the Kafka console consumer. Here we can see that in the middle terminal, we can see that now the topics list also shows the test topic, which is created when we started the producer client. And here we can see that we have started a Kafka console consumer, which will consume from the beginning, and we have already received the first message. Now I am, for demo purpose, I am sending another message, and that message is also consumed, as we can see in this demo. So that is the demo of KOP. Now we will go ahead to the next. So as we know, Kafka has a lot more connectors than Pulsar. For Pulsar, standard connectors like Spark connector, Flink connector, Elasticsearch connector, Presto connector, those are available, but still there are a lot more connectors in Kafka than Pulsar. So to go get around that, what we have done is we are using KOP enabled Pulsar cluster with the Kafka connectors to achieve Pulsar connectors. So one of such connector we made is Pulsar Druid connector. So to achieve a Pulsar Druid connector, as Druid was already supporting Kafka, so they have a Druid Kafka connector already. So when we enabled KOP on our Pulsar cluster, when we produce live events from Kafka clients to our Pulsar cluster, that also reflected so that end users can query the live data. So for this, I will, as the image also depict the same thing. So for this also, I have a demo. So now we will go ahead with the demo. So first I am extracting the Druid binary, and I am taking the latest version for this demo. So it is 24. So inside the Druid binary, it provides, so Druid has the concept of data source. So it provides a Wikipedia data source by default, which contains events of live Wikipedia edits of one day. So I am just on entering that data source file. So now I will put this one day data into KOP enabled Pulsar cluster. As you can see, we are using the Kafka console producer and we are giving the KOP enabled Pulsar cluster broker URL, and the topic which we are creating is Wikipedia. So this will what this command will do is it will take all data from this JSON file and put each event inside the Pulsar topic. So as we can see here in the middle terminal, when we are listing the topics, the Wikipedia topic is now created. So now we will go to our Druid console and we will configure with Apache Kafka streaming data using this KOP enabled Pulsar cluster. So here we are giving the broker link as Pulsar cluster, the topic as Wikipedia, and for all other steps, I am taking the default. So here I have selected the segment granularities as hour, so that as we already mentioned, we have one day data, so it will create 24 segments out of that. Here we are setting the earliest offset to true, so that it will start consuming data from the beginning of that topic. So now in the final step, what it has done is it has created a spec. So in Druid, this is called a supervisor spec. So this spec Druid will submit to the supervisor spec. Druid will submit, and that will in turn create a index task. So that index task will monitor for the live events. The existing data also it will put in Druid. As you can see, the existing data is already put. So it has created 24 hourly segments out of the one day data. So these are the intervals of 1 hour each. Yeah, we can see the index task and the supervisor both are running now. Now what we will do is we will try to produce some live events and see if that is going to Druid. So here we are using the Kafka console producer and we are putting an event with the current date. So as you can see, as soon as we put the data, it has created another segment in our Wikipedia data source, and now it shows 25 segments. And before ending this demo, we have, yeah, so here it has added one more row to the segment of the data source. So now we will just see a live query of our recently inserted data. So here I am just querying for the live data. Yeah, as we can see, the comment we added earlier, that is added live data. So this ends the demo for Pulsar Druid connector. So this way we can use KOP cluster to make multiple connectors. So yeah, so these are the references we used for making this awesome slide. And now we are open for questions and